So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quantum Mathematics. I'm Aman, just welcoming you all to a new amazing video in which we are going to talk about the proof of this most basic integral in integration ever. So, basically, we have talked about the wait a sec. Yeah, so far we have talked about the most basic integrals proof of six most basic fundamental integrals. So I have made a playlist over on that, so you can just check that out if you want, right? So for now, let's just consider this integral. And you know what? Have we have ever studied integrals, and if we got to see this, so we haven't asked any questions like why does this happening and why does this integral evaluates to x to the n plus 1 over n plus 1. We just have to memorize it, like our teacher or professor or anyone just make sure that you don't ask questions. For this is a lemma, this is a something like true for universal truth, something like that. But we are not here to just accept the truth, we are going to just prove this down, right? Why does this happening? Because it didn't came out of nowhere. So we're just going to take a look at the proof of this thing, right? Okay, so basically what we are going to do here is we are going to compare this something like this: the integral of small f of x dx equals capital F of x. So for if we compare this with this and this with this, so basically we're having small f of x equals x to the n, and capital F of x comes out to be x to the n plus 1 over n plus 1, right? So yeah, that's what we are having here, right? Okay, so you know what, the integral is known as the antiderivative of this function, right? So I'm sorry, the antiderivative of this function is x to the n, right? Oh, I'm just messing up here. I'm sorry, the antiderivative of x to the n is x to the n plus 1 over n plus 1, and the derivative of x to the n plus 1 over n plus 1 is x to the n, right? Yeah, it's pretty fine now, it's fine, I'm sorry about that. Okay, so now let's just consider proving this out here. So basically we know that if we take the derivative of the capital F of x here, I'm sorry, yeah, capital F of x here, so it's a d over dx of x to the n plus 1 over n plus 1, right? So basically it is 1 over n plus 1, and if we talk about the chain rule here, so that is um n plus 1 times x to the n plus 1 minus 1. So basically we would be getting rid of n plus 1 over n plus 1, that is 1, and this one cancels out with this one, so basically we're having x to the n here. So that's it. Hence the derivative of this one is x to the n, and the antiderivative of x to the n is x to the n plus 1 over n plus 1, right? Okay, but how did we know the derivative of this one is this? So let's just prove that down here, right? Because we are here to prove everything, not consider anything, right? Okay, so basically it comes from the definition of the derivative that says f dash x equals limit h tends to 0 of f of x plus h minus f of x over h. So this is the definition of derivatives, right? And yeah, it's pretty needed to remember this, and you can just prove that down even if you want. You just have to take care about some graphs. Okay, so now we are gonna here I'm sorry, we are gonna set here f of x equals x to the n. So we are here actually we are going to find the derivative of x to the n here. Let's talk about the derivative of x to the n. So it's limit h tends to 0, I'm sorry, h tends to 0, and when we replace x with x plus h here, so that's gonna give us x plus h to the n and minus x to the n over h. And now we know about the expansion of this thing. So this is the binomial expansion of x plus h to the n. So x plus h to the n can also be written as in terms of binomial expansion, something like this: x to the n plus n x to the n minus 1, and it's h plus, I'm sorry, yeah, it's wait a second, yeah, n times n minus 1 over 2 and times x to the n minus 2 h to the 2, and plus this keeps up to I'm not I'm just messing up here. Let me just clarify that. So it goes up to h to the n. Yeah, it's pretty fine. Okay, so this is the binomial expansion of this x plus h to the n, and again it's pretty needed you to just keep it in your mind, because it's gonna help us a lot of times in mathematics if you're gonna expand some x plus y or something to power. So it's pretty needed here. So let's just replace our x plus h to the n with this big chunk of thing here. So it's limit h tends to 0 of, when we replace it with that, so it's x to the n plus n x to the n minus 1 h plus n minus 1 over 2 times x to the n minus 2 h to the 2 dot 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 to in I'm sorry, not infinity but h square. Actually I'm getting some sort of addiction to infinity, so that is why I'm like just writing infinity every time, and it's minus x to the n over h. So now here we are successfully getting rid of this x to the n and x to the x n terms. So basically we are having f of x I'm sorry, f dash x equals limit h tends to 0 of well, we can consider taking h common out of this, because we are having h in every term. And I'm sorry, I did mischief here, because it is h to the n. Yeah. So when we can consider h taking out, so it's n x to the n minus 1 plus n times n minus 1 over 2 x to the n minus 2 h dot 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 2 h to the n minus 1 over h. So here we are successfully got rid of h, and when we plug limit h tends to 0 in all of these cases, so these cases are gonna be 0, and basically we would be left with f dash x equals n x to the n minus 1. And hence proved, guys. This is the chain this is the sorry, I'm sorry, it's the power rule of the derivative. That is, the derivative of x to the n is n x to the n minus 1. That is what we have used it in our proof of that integral. So yeah, that's it guys, and I hope you got to know something from this video. And yeah, I just messed a lot of times in this video, so I'm really sorry about that. I'm extremely sorry about that, but still, if you got to learn something from this video, please make sure to like, subscribe and share. And if you have any kind of doubt, so please you can solely ask me in the comment section at any time, and I will make sure to just reply it as soon as possible. So yeah, it's pretty fine, and thank you so much for watching this video guys. Goodbye, take care, love you, and let's just get back to the next video for some better and beastie things. Goodbye guys, take care.